All right, topic 8.3 today. Accumulation functions are very common on the AP exam. And we've talked about the fundamental theorem of calculus. And the fundamental theorem of calculus is the one that relates the antiderivative of f. And if we integrate a function, we are finding the antiderivative. And then to find the exact value, we do f at the top limit minus f at the bottom limit. All right? We've done that for a while. The net change theorem, all right, is a little bit different. It's saying that the integral of the derivative is f of b minus f of a. Now, if I add, look what happens if I add f of a. If I add f of a to both sides, I get what is called the accumulation model. The accumulation model with the definite integral. If f of a is known and the rate of change between a and b is given by f prime of x, then we have this accumulation model, all right? And so this can tell me the value of f of b, all right? Now notice something, I could do some algebra with this, all right? I could subtract, so this is, put a box around this, that's very common on the AP exam, this accumulation model. But also note that if I subtracted the integral from both sides, I could have that f of a is equal to f of b minus the integral of the function. The integral of the derivative of f, that is. So the best way to see this in action is to do an example. And let's go ahead and look at one. A function is known to be increasing at a rate modeled by f prime of x equals 3x plus the sine of x. It is also known that at x equals 4, the function has a value of 15. That means that f of 4 equals 15. We're going to need that in a minute. All right? Find the value of the function at x equals 7 and x equals 2. All right? So, what I know is that I'm working with an integral from 4 to 7. Okay? And if we follow our accumulation model plan, all right, we're going to integrate the derivative. We're going to put our function value at the top limit by itself. So I'm going to have my f of 7 over here, and it's going to be equal to f of 4 plus that, plus the integral of f prime of x, which they give me, 3x plus the sine of x dx. To be honest, if you know the accumulation model plan, this is pretty easy. It's really just kind of plug and chug. All right? Plug your values in and chug through the problem. This is definite calculator problem. They told me what f of 4 was. They told me f of 4 was 15. And then I can use the TI-84 over here. And I'm just going to tell you what that value is so we can get through our other problems. It's 48.092. And I get the answer is 63.092. That is f of 7. Now, they also told us to find the value of the function at x equals 2. All right. Well, if I'm going to do that, then I'm working at a bottom limit of integration. That's why I showed you this form right here. Okay? This form, this is the bottom limit. And you might be asking, how do I keep all of this straight? The best way to keep all of this straight is with this thing right here. Because if you can remember this right here, then you can do all the algebraic manipulations you need to get it into whatever form you want. All right? So this time, we are working at the bottom limit of integration. All right? So I want the f of a to be by itself. All right? So if I do my algebra to get f of a by itself, then I have that f of a equals f of b minus the integral from a to b of f prime of x. All right, and I've already showed you how we can do that algebraically. So my bottom limit of integration here, in this case, is the 2. So I'm going to be looking for f of 2. And I have to work with values that I know. All right, and the value that I know is f of 4. I don't want to work with 7. Okay, now we did just find f of 7. You know, we could have done that, but they gave us f of 4. We may as well work with that. Minus the integral from 2 to 4 of our 3x plus sine of x dx. And once again, we can just figure that out with the TI-84. It's more about plugging in to the accumulation function the right way. So if we know an initial value of a function and the rate of change of that function, then we can use that to find any other value of the function on that segment. All right? Let's look at the tank of water problem. A tank of water is leaking at a rate modeled by v prime of t equals that ugly function. This thing right here. Where v is measured in gallons and t is measured in days since the leak started. No water is being added to the tank, and the tank held 24,000 gallons when t equals 2. This thing right here is our initial condition. That means what they told me right here. V of 2 equals 24,000. How much water is in the tank 4 days after the leak started at time 4? All right? So once again, already got it written here. There's our accumulation function formula. I want to find V of 4. All right? They give me V of 2. And I want the integral from 2 to 4 of the rate function that they gave me, that negative 25 pi over the square root of t dt. All right? They give me the V of 2. Remember, we have to know that initial condition. We have to know that to be able to do these problems. So they give that to me. It's 24,000. This, I'm going to tell you, notice it's leaking. The water is leaking. So when you do this on the TI-84, you get a negative value, negative 92.015, according to the TI-84. That would be math 9. And we get this correct answer of 23,907.985 gallons. Remember something about our decimal answers on the AP exam? Our answers are always rounded or truncated to 3 decimal places. That's what they require. Rounded or truncated, which means cut off at 3 decimal places. Another problem. A printer is publishing multiple copies of a specific document. While printing this document, ink is being used at a rate of this, measured in ounces per minute. If the printer started the job with 5 ounces of ink in its cartridge, how many ounces of ink will remain in the cartridge after 3 minutes? All right. So in this case, they started off with 5 ounces of ink. All right. So that's why this turns into a subtraction problem. All right, because ink is being used. So we would do the integral from 0 to 3 of my rate function, 0.2, times 1 plus the cosine of t dt. All right? Most of this is just knowing where to put the numbers in the accumulation function and knowing whether to add or subtract. When you do this on the TI-84, you get our correct answer of 4.372. All right? This is a tabular type problem. And this is very common on the AP exam for them to give you information in a table. Does not make it any harder. It just means you need to know how to attack it. An oil tanker is in port and being filled with oil. A table of values is shown with observed rates of oil being pumped in over an interval of 10 hours. All right. 2 hours into the interval, there are 110,000 barrels of oil. All right. So that right there is an initial condition. Use a Wright-Riemann sum approximation to estimate the amount of oil in the tanker at the start of the 9th hour. So I've got it kind of copied and pasted here. Right here is how we plug in. This is what we're looking for. We want to start with our initial condition. Okay? Here is our value, my R of 2. Okay, right here. And then we need to do the integral from 2 to 9. Okay? Now, here's what's different about this problem. This is not a TI-84 problem. They did not even tell me the function. They're asking me to use a Wright-Riemann sum to do the integral portion. All right? So we're going to use a Wright-Riemann sum, all right, and we're working from this area right in here, okay? So on the first one, which is involving this right here, I'm going to do 4 minus 2. That's going to be my width of the rectangle. And I'm going to multiply that by, remember when we do Riemann sums, we use the function values. So I'm going to use the right value. So it's times 75. And then I need to go to the next two. Go to these two. So that's going to be 7 minus 4 times the right edge, which is, again, 75. And then I'm going to go to the next two, which are these two. and I'm going to add 9 minus 7 times the right value, which is 70. My bracket up here should have started at 9, by the way. We don't need to go over to 10. And then I need to add 110 to that, because that's what we said in our accumulation model. All right? And if you do your algebra correctly on that, you get 625, but remember, we were supposed to be in thousands. And this last problem is a graphical representation. All right? A balloon, let's read through it, and then I'd like for you to kind of work through this one on your own. A balloon is being used to move sensors to different altitudes and is anchored to the ground by a cable on a winch. The graph, made of 3 line segments, that could be important, represents V of t. Okay? So the 3 line segments that we have here are V of t. Represents the rate at which cable is being let out or pulled in over an interval of time. At t equals 0, here's our initial condition. The balloon has an altitude of 10 meters. So t of 0 equals 10, and you'll see that represented right here. Assuming the balloon moves straight up and down, find the balloon's altitude at time t equals 540, which is 9 minutes after the experiment begins. So it is just a, how do I do this integral now from the graph? This is all they gave me. We have to basically calculate an area, all right, from 0 to, if you can't see it real well, that is 540 right there. All right, and I'm going to tell you the correct answer so that you can try to work through that on your own. The correct answer should be 22,510. But it is essentially just a, remember, anytime we are finding an integral, we are finding area under the curve. So it's just an accumulation function problem, but how we actually find the integral is a little bit different. And we're going to stop there for today.